So, before we do anything, maybe first announcement of note is, let's see, how many people have started in on the induction homework at this point? How many people have noticed the problem in the list? Well, I guess at least one problem in the list which is false, as stated. You did. Item 3, I think, is just like false, right? When you plug in n equals 1, which is allowed, you get 2 is less than 2? Oh, well, that's not true. So, this problem should then be changed, right? Here is the tweak that I will say to make. It's up to you exactly how you choose to incorporate these instructions. Make as small a change to that statement as possible while resulting in something that seems to be true. Then prove that statement using induction. Oh, I guess that makes it particularly important that people on that problem 3 really explicitly state the thing that they're going to prove. And a lot of people got the warning message from me on their homework saying, state the thing you're going to prove. Because I'll start taking off points starting this one, especially on 3, because you get to pick what thing you're going to prove now. That bit of instruction make sense? Cool. I think the other thing on the to-do list from last time is I gave an absolutely dumb warm-up exercise last time, right? Dumb in that I told you to use a proof technique that was significantly more complicated than the simplest possible one. So, I want to start, not with this as homework or anything. I don't want to collect it. Here is a different claim. I claim that for every natural number n, as long as n is bigger than some threshold value, and I don't know what that is, we'll figure it out, n can be written in the form p times 5 plus q times 2. So far exactly the same conclusion as was in that thing I had to do last time. But this time p and q are required to be natural numbers, not just any integers. This isn't in the notes anywhere. This is me figuring something out on the spot. Well, I guess before we can prove the claim, let's try to come up with the claim should even be. So this would, I think, not be part of what you would submit as a proof. Let's start listing numbers that you can write as a non-negative multiple of 5 plus a non-negative multiple of 2. Can you do n equals 0? Yeah, how? When n equals 0, what p and q seem to do? I think those will do. I think that's even the only way. N equals 1? I think not, right? And maybe a better way to do this is, let's just start taking choices of p and q and seeing what we get. P is 0, q is 1, what do you get? P is 1, q is 0, what do you get? So 5 can be done. I guess the next choice is 1, 1. And let's ratchet things up like that. What do you get out of that? And now let's allow them to, how am I choosing to organize this? One's where the total sum is 1. One's where the total sum is 2. So 2, 0. 10? 0, 2? Okay, so let's just start putting this on a number line. 0 is good. 1 we haven't seen yet. 2 is good. 3 we haven't seen yet. 4 is good. 5 is good. 6, 7, 8, 9, 10. We've got 10, we've got 7, and let's see what more we can do. So anyway, just like keep on filling in this table. Now let's see what patterns you start to notice about what things might not be possible and what things should be. Once you've got some like intuition about what numbers will eventually get check marks and which ones won't, let's hear it and discuss with each other too. Zeros in. Has anyone managed to get 1 to appear on the list? And do you think, can it possibly appear on the list? No, you add some 2s and some 5s together, you're going to get something that's at least 2. Other than 0, but we've already seen that, so that's out. How about 3? Alright, I guess what's the logic? Well, you certainly aren't allowed to use any 5s. But if you're not allowed to use any 5s, you can't get something odd. So I think 3's out. 4 is good, 5 good. Can you get 6? How'd you get 6?
It's 5p plus 2q, right? Is that what it's written about?
Yeah.
Okay, then I got it from p equals 0 and q equals 3.
Cool. I'll write that as 2 times 2 so I don't have to deal with which one's p and which one's q. How about 8? Cool. I guess like 4 times 2? In fact, I think you can get anything even, right? Yeah. That's what even means. How about 9? How'd you get 9?
5 times 1 plus 2 times 2.
Oh, neat. So, at least based on this sample of ending at 10, it looks like everything starting at 4 seems to be in. Let's try to use this to make a proof. So I think the way that I would choose to organize this, at least in terms of Scratchwalk, if I don't already know the proof, would, I don't know, how many people have already just like seen this sort of thing in the past? Oh, cool, good, okay. So no one is like totally bought and already knows what's about to happen. Let's try to come up with the inductive step first. And then we'll figure out what the base case would be. There's no law saying you have to write the base case first. And I guess according to this table, the base case, since I'm going to do strong induction, could be every n between like 4 and 10. So let's start with the base case. Nope, inductive step. And let's write down the thing we get to assume. We will get to assume that n is greater than or equal to some threshold value. And then let's also assume for all j in the naturals, if 4 is less than or equal to j, since 4 is when this thing starts to appear to be true, is less than n, then J equals P times 5 plus Q times 2 for some P and Q in N. All right, so I know that everything less than N, at least 4, can be put in this form. Now I need to put N in this form. Let's see. So I know how to do stuff with like 2 and 5. If you add 5 to something that's a valid number here, you would just ratchet up P by 1. If you increase by 2, then Q would go up by 1. So tell me, how can you express N as something that's a little bit less than N plus either 2 or 5? Yeah, cool, that'll do. N is equal to, and I'm going to do some color coding, just normal. N minus 2 plus 2. All right, so let's stare at this for a moment. I'm going to leave myself some space here. I'm going to need N minus 2 to be less than N. Is that obviously true? All right. I'm also going to need it to be bigger than or equal to 4, since the claim only starts being true at 4. Oh, cool. So how big do I need N to be?
6.
Yeah, right. Cool. Let's assume that N is bigger than or equal to 6. Let's see, since N is bigger than or equal to 6, we get that. So, by our inductive assumption, N minus 2 is equal to P times 5 plus Q times 2 for some P and Q in N. All right, so we already had like the plan, right? The point is that N is now something that we like plus 2. So now let's just finish it up. Given what is written right now, how can you write N as P times something times 5 plus something times 2? Yeah, awesome, right? P times 5 plus Q plus 1 times 2. And I think I'm not going to finish writing. Like at this point you would say, and so we have now verified that N can be written as a natural number times 5 plus a natural number times 2. This completes the inductive step. Thus, by the principle of strong mathematical induction, we conclude that blah, 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 blah. How'd that feel? And in fact, like this is obviously generalizable. There was very little special about 5 and 2 here. So here's maybe like a fun question to think about. If I give you a P and I give you a Q, you can do something like this probably. You figure out the details now. In fact, I think that'd be a perfectly viable challenge problem that's not in the notes anywhere. Cool. How'd that feel as something you really need strong induction for?
I feel like you could do that without strong induction.
Cool. Come up. What do you have like a plan in mind?
No.
All right. Cool.
Think about it.
Yeah. yeah, theoretically, any inductive proof you could prove, since as we talked about, strong induction is like the same as the well ordering principle. You could scrap this proof structure and instead say, well, I'm going to let x be the set of all natural numbers such that this happens. Now I'm going to try to like study the minimal element of x and come up with a plan. And then it wouldn't be inductive, but it would be like the same as inductive. So yeah, try to come up with something that's really not inductive. Cool. All right. So that was just like filling in a gap. I'm going to switch gears quite a bit because now I'm going to jump back into the notepad about the integers. Although something similar will happen soon. And let's just start by remembering what we proved last time. So what did we do last time? We introduced the idea of the well ordering property. One way to prove things about integers is by studying a set, proving that that set's non-empty. Then you know that that set automatically has a minimal element. That's by the well ordering property. And what did we use it to prove? We used it to prove this division algorithm. If I give you two integers, d being bigger than or equal to 1, a numerator and a divisor, then there's a unique quotient and a remainder. So that n is quotient times divisor plus the remainder. And the remainder isn't too big. So we did that last time. I want to start by doing just some easy stuff. Let's write down some definitions and state a reasonably straightforward theorem. All right, if I give you a d and an n in the integers, d for divisor is a divisor of n, and I write d divides evenly into n. Yeah. Well, what do you think that should mean? Oh, cool. Yeah, let's, in theorem 2.1.1, r is 0. Yeah, that seems reasonable. But let's write down a statement of this that doesn't require you to flip to the previous page and read a theorem to figure out what the definition is now. So I guess that means r is 0. So there is some q, which satisfies that n is equal to q times d. That seems reasonable, right? And there's another way of saying the same. This means that n is a multiple of d. Oh, but of course it does, right? There's nothing fancy there. That's what it means to divide into something. So let's state some things. And at this point, you've probably been in a class where this symbology has been used at some point. Since it takes too long to say d divides into n, I'll just put like a vertical line there, and you're supposed to read that as divides evenly into. How many people have seen that notation at some point? Yeah, okay. I bet you have, even if you're not raising your hand. So, let's state some things about this. This relation, divides evenly into, is symmetric. For every natural number n, n divides evenly into n. Do you agree? Yeah, because n is 1 times n. Transitivity, if d divides into m and m divides into n, then d divides into n. What do you think? Fair enough? And even like, I think that should feel pretty obvious. Cool. Almost anti-symmetry. If d divides into n and n divides into d. So anti-symmetry would want to say that basically can't happen. But it can happen, right? N divides into itself, so it's not totally anti-symmetric. And in fact, n divides into minus n. But that's it. This almost anti-symmetry condition says that if d divides into n and n divides into d, then d has got to be plus or minus n. Divisibility in linear combinations. If d divides into m and d divides into n, then d divides into any integral linear combination of m and n. And what do you think? All of those seem reasonably obvious? So there's some stuff written down here proving the thought of the claims. Do you think we should spend time on it? How many people think that they could come up with all of those proofs directly just by staring for 5 minutes at it. Okay, not seeing confidence. Let's prove item 3. And it's just going to be like a definition chase, followed with like one step which will be believable, but we haven't justified. So let's prove the thought. Let's consider any n and d and z. N and d are the only variables that appear in 3. Let's assume that d divides evenly into n, and n divides evenly into d, and now let's just remember the definition. The definition of a divisor. Now lets us conclude that there are some integers, k and l, which satisfy that. Look back to the previous page if you need. If d divides into n, then what do you get? Yeah. D equals like kn, and n would equal ld. Yeah. Oh, cool. So now I'm gonna like, no, I'm not allowed to use the board today. I want to record everything. D equals kn, n equals ld. And I don't know, we've got 2 equations now. Let's just muck around and see what intuition strikes us. So if d is kn and n is ld, do something with that. I don't know. Imagine I asked you to like try to solve this equation. Because that's kind of what I did. I don't know, the box just tells me what d is equal to. So if I wanted to like solve this for n and d, then I've already done all that part. So like, I don't know, the like high school algebra brain says, well, back substitute, right? I already know what d is, let's substitute that in, and we'll just see what happens. And this is just like scratch walks, I'm not going to worry about wads. So that means n is L times K times n. All right, what can you do with that? Yeah. Great, yeah, divide both sides by n. So now I have 2 integers that multiply together to be 1. And this is where like the thing that's not going to be justified. So since the only divisors of 1 are 1 and minus 1, what can you tell me? Oh, cool. So k and l are either both 1 or both negative 1. Let's see, if it's 1, then d is n. If it's minus 1, then it's minus n. Oh, that's what we wanted. Okay, cool. Let's put that into wads. So let's see. Let's start by plugging d equals kn, which is a thing that we have written down, into n equals ld. We get n equals L times K times n. So 1 is equal to L times K. So K and L are divisors of 1. Thus, as you said, either k equals L equals 1 or k equals L equals negative 1. If k equals L equals 1, then d equals n, k equals L equals -1, then D equals -1. Either way, we're done. And there's more than one way to write any of that, but I think there's one way. Cool. That seemed pretty all right. And all the rest of these claims, this in some sense is like the hardest of the lot of them. The rest of these claims are algebraic proofs that just require you to write down the definition of a divisor and do some stuff with it. This one had like this gap where the only divisors of 1 are 1 and -1, which you know. But cool. How'd that go? That seem okay? Nice. Any questions so far? All right. I guess one of those is assorted to be like a homework question. Yeah. So, I think probably the rest of today we'll wind up talking about common divisor as the notion of GCD and a fact that you might know, which is discussed under the name Bezout's identity. Let's write it down. So definitions. If I give you two integers m and n and d, we say d is a common divisor of m and n if what happens? Nice. And that's one of the reasons that I want this vertical verb, because divides evenly into is a lot of things to write. The greatest common divisor, denoted GCD of mn, is the natural number. It says only a natural number, so we'll have to do something about uniqueness. Satisfying the following conditions. D is a common divisor, meaning D divides into m. It's not called D, it's called GCD. No, it's called D. D divides evenly into m, and D divides evenly into n. And it's called the greatest common divisor. So, like, what's the most intuitive thing you could think for the other condition to be? Yeah, right, that's all. It'll turn out that's not what I'm going to put in the next line, but the most obvious, but it turns out less useful definition is exactly that. D is less than or equal to, D prime is less than or equal to D for every common divisor, D prime. The one that I'll actually use is the one where you think of dividing into as being your sense of inequality. So here's the actual statement that I'll give. Any common divisor of m and n is a divisor of D for all D prime if D prime divides into m and D prime divides into n, then D prime divides into D. And I don't know, people would rather see a different variable there instead of D prime. Yeah, okay. It's all a matter of how much you trust your font. If your D primes look different enough, then keep it. Otherwise, replace those D primes with E's. So, let's see. An advantage of this definition is it like obviously exists. If I give you an m and n, there's at least one common divisor, namely 1. And they're like bounded above by something, right? Like m plus 5 can't be a divisor of m, so it can't be a common divisor. So like the well-ordering principle will let you conclude that this thing exists. Getting this to exist will take a little bit of work. But it turns out this condition will be like more useful. And maybe just in terms of like getting intuition, let's check that they're the same. Actually, no. With the time allotted, exercise for you. Check that the greatest common divisor is in fact a thing that divides, every other divisor divides into, and is at least as big as every other divisor. Not homework, just something you should do on your own. So, it's not so obvious that something satisfying this condition should exist. Right? If I give you a bunch of numbers, I mean, you can find something that they all divide evenly into. But it's also got to be a divisor of m and n. That seems like it might be dicey to arrange both at the same time. So we need to prove that the GCD even exists using this definition. This theorem will show that the GCD exists and in fact give us a classification of what it looks like. So here's the theorem. For any m and n in Z, the GCD of m and n exists, and, don't need this then, and there are some x, y in the integers with GCD mn equal to xm plus yn. So not only does the GCD exist, the GCD can always be written as a multiple of m plus a multiple of n. And let's try to do it. So this is going to be another proof based on the idea of the well-ordering principle. Let's start by letting capital X just be all of the natural numbers that you can write in this form. That seem fair enough? So we will show that for some choice of x and y, xm plus yn satisfies the definition of GCD. I'll let big X be the set of all of them. So let's let x be the set of all xm plus yn such that x and y are integers and xm plus yn is in the naturals. Right, because the GCD is going to be a natural number, it has to be. Yeah, GCD is a natural number as required in the definition. So let's study the set big X. Is that set big X a subset of the natural numbers? Yeah, it says so in the definition. It's things that look like this, and one of the conditions is that thing has to be a natural number. Obviously a subset. Now I need it to be non-empty. So let's try to get this sucker to be not the empty set. Is that what I want? I'm going to add one more condition. I'm going to make it be bigger than 0. Just as I think 0 would be bad. 0 shouldn't be the GCD, but 0 is definitely in this set. So I need the set to be non-empty. I need to produce something that's in this set. So, how would you want to do so? Can you guess a way of starting with? No, in terms of time, let's not play guesswork. So X is a subset of n. You can write down some stuff. But I think it's more or less obvious. Let's try to get X to not be the empty set. So I need mx plus my to be at least as big as 1. What trace of x and y would you like to use? Well, possibly by cases. You could just use 1. 1 and 1? Cool. I think that'll walk as long as they're both bigger than 0. Which is not part of the assumption. What if they're both negative? Then what would you use? Both negative 1? If one's positive and the other's negative? Mix a 1 and a negative 1? So I think cases Or maybe like the sneaky way is n squared plus m squared. Well, that's going to be positive. Cool. So it's like really sketchy, but we get the idea. So by the well ordering principle, this set is not empty and is a subset of the natural number, so what can we conclude? Not that it has an order. There's so a different thing that's also sometimes called the well ordering property, which is in like set theory, which says that if you give me absolutely any set, there exists a well ordering on that set. And a well ordering is just something that satisfies the thing that on the previous page I said is the well ordering property. Or maybe 2 pages ago. Oh, nice. Yeah, that's it. So whenever you appeal to the well ordering property, you're just going to take the smallest element. By the well ordering property, X has a minimal element called D. And I'm saying D because I'm about to call it D. So let D be something that looks like mx plus ny with x and y in the integers, which is the minimal element of x. Feel pretty good? So what do we need now? I need D to be a common divisor of m and n, and I need every divisor of m and n to divide into D. So we just need to do both of those things. First, we will show that D is a common divisor of m and n, and then at the end of the proof, we will show that every common divisor of m and n divides evenly into D. So let's try to do it. So, well, there's some guidance here. Let's proceed by contradiction. If I want to show that D is a common divisor of m and n, what do I get to assume? It's not a common divisor. And I don't want to just like straight up write that because that's like not useful enough. So if D is not a common divisor, I'll flip to the previous page. That means this must not be true. So if this statement with an and is not true, what can you tell me?
Either one is not true or the other.
Yeah, at least one is false. So either D does not divide evenly into m, or D does not divide evenly into n. Where here I'll introduce yet another notation. When I have a symbol that denotes something, if I draw a line through it, it means I'm saying it's not true. Which is a convention you already know, right? From like not equals. And without loss of generality, let's assume, I don't know, D does not divide evenly into m. I bet if we could come up with a proof when it doesn't divide into m, we could just replace all the m's with n's and get a proof when it doesn't divide evenly into n. All right. So let's play this game now. So by the division algorithm, there's some q and r in the natural numbers, so that m is equal to q times d plus r with 0 less than or equal to r less than d. And that's just the statement of the division. All right, I want to get a contradiction out of this. And the contradiction I want to get, I think, is going to come from isolating r. That's easy enough to do. So r is equal to m minus qd. But wait, but I know that D is in the set big X, right? It's the minimal element of big X. As D is in big X, D is equal to xm plus yn for some x and y in Z. Ah, but that means R is now equal to m minus that. So let's see, can I do subtraction? 1 minus x times m. Nope, 1 minus qx times m. Because this gets multiplied by q and then subtracted. Yn becomes minus qyd. Ooh, so this R is also in the set big X then. That's a linear combination of some m's and some n's. I claim that's a contradiction. Why is it a contradiction for this R to be in the set big X?
Because R should be the remainder.
R should be the remainder.
If it's in big X, then it divides into M.
Well, not quite, because it's a linear combination of the two of them. So it doesn't need to divide evenly into either. So remember, D was supposed to be the minimal element of big X. So D should be the least thing in big X. But the division algorithm produces an R that's less than D. Since R is less than D, this contradicts that D is minimal. Cool. And that's like a standard sort of idea. If you're using the well-ordering property and you're making a proof by contradiction, that's a thing you should be trying to contradict. You're going to try to build something in the set big X that's a little bit smaller. And now let's finish it up. Now we need to show that every common divisor of m and n divides evenly into D. Let's put it strictly less than there, because otherwise we're not negating that D divides into m. Now we need to show that every divisor of m and n divides into D, and I think this is one that's like more or less automatic. If D prime, no, I don't have enough space for the apostrophe. If E is a common divisor of m and n, then, well, E certainly divides into anything that looks like xm plus yn. Oh, but D is exactly at that point. Oh, cool. So there's like some sneaky steps in there. What do you think? That proof more or less followable? And it unlocks, this last thing we're going to do is going to be something that will be computational. Let's talk about how you can train a computer to compute the GCD by using this trick as a starting point. So here's some facts about GCD. First, if I give you any m, what's the GCD of m and 0? And maybe we'll see this, just write this explicitly. What's the GCD of 5 and 0? What things divide into 0? And it's like a weird choice, right? Go to the odd. 2 divided evenly into 0, so let's see, that would be, is 0 equal to 2 times something? Is it? Oh, cool. Is anything not a divisor of 0? So 0 is like a special number. Everything divides evenly into 0. We've seen that very few things divide evenly into 1. So 0 and 1 are very different from the point of view of GCD. So let's put that into this language. So GCD of m and 0. Just m? If I flip the order of m and n, I don't change the GCD. Agree? Yeah, the definition of GCD is totally symmetric. This one's complicated looking. If for any m, comma, d, comma, q, comma, r, the GCD of m by quotient times divisor plus remainder is the same thing as no, erase that d, replace that with if I take a number r and increase it by a multiple of m, I don't change the GCD of m in that number. That's all that this is saying. What do you think? Is that more or less, is that vaguely believable? And I claim that all of these statements are enough to algorithmically compute the GCD. And let's just do this once. And it turns out this algorithm is more efficient than just listing all the divisors of one and all the divisors of the other and finding the biggest of the lot of the common ones. Because that's like really slow. If I ask you to list all the divisors of 1,376, right, you can start somewhere and like build them, but it's going to be kind of slow, especially for a big number. Here's an algorithm that's a little bit faster just to find the GCD. It's still not super fast and kind of can't be. So here's one algorithm. So if I want to compute the GCD of 1, 2, 3, 4, 5 with 1, 2, 3, well, first I can write 1, 2, 3, 4, 5 as 1, 2, 3 times a number plus 45. If you like, that's just the division algorithm, right? Oh, so that means GCD of 1, 2, 3, 4, 5, comma 1, 2, 3 is just the GCD of 45, comma 1, 2, 3. That look easier to compute? Let's do it again. The bigger of the two numbers, 123, is something times 145 plus a remainder. And I guess to find that, you'd have to like do long division. That's kind of annoying, so I think I'm going to like try to do it quickly. I think 45 goes in there twice, and that's like 90, the remainder is 33. So GCD of 45, comma 1, 2, 3 is the same as the GCD of 45, comma 43. And what do you think? Is this getting into the range that you think you can just eyeball the answer? If not, great. That means you have motivation to run this algorithm again. So do it again. So I guess that would be saying 45 is something times 33 plus something. So the GCD I want to compute of 45, comma 33 is the same as the GCD of something that's smaller than 45, comma 33. I got like a minute. So what you got? What do you eventually have going in that blank? I think I'm getting 18. That is one copy of 33 plus I think 18. 18 comma 33. Do it again. You'll see that this is the same as the GCD of 18 will stay the same. 33 will change. It becomes, gosh, 15? And what do you think? Does this look like an algorithm where those numbers are continually getting smaller?
Isn't that 12 but not 18, or am I?
Thank you for catching me. guess that'll affect the next step. Now I want this thing to be 15. So, I don't think I'm going to finish this out. Eventually I'll see, staring you in the face, the GCD of 0 and 3, if you repeat this algorithm. Oh, what's the GCD of 0 and 3? It's 3. So, here's closing comments for today. Do the same thing for the GCD of 5, 4, 3, 2, 1, comma 1, 2, 3. Use a computer to do the division steps if you need. The first couple division steps after eventually, like, the numbers get small, right? How many people in this room are vaguely computer science minded? Maybe you took the data science class, you liked it. You've taken a few computer science classes and you've liked those. Do you think you could write some pseudocode for this? Maybe even some actual code? Oh, cool, do that. That's a challenge problem. Run it for some examples. And this is, in fact, the most efficient way to compute the GCD. It's more efficient than trying to find all of the divisors of each one and finding the biggest of the commons, because it turns out it's actually quite hard to find divisors of a number that's really big. And that's one of the premises on which modern cryptography is based. Cool. All right. Well, as is usual, I'm bad at ending class on time, and bad at having a structured end to class at all. I've also fallen behind schedule, so expect the schedule to be updated. Ooh, anyone planning on coming by my office hour today? You are, right? Don't you have anything you need to make up?
I'll be there Friday.
Friday, okay. Stop recording.